All right. Good afternoon, everybody. This is Jeff, Bon, and I'm Taole. We're part of Nahmad Bhooshan studio, which deals with the future of living and mass customization in combination with computational technologies. We're proposing a negotiated commune system that provides custom-tailored homes to cohesive communities based on their existing social networks in order to establish sustainable local communities. Using a relational model, our project looks at generating buildings based on social relationships in a community. On the next scale down, we're proposing a customization system where the housing configuration is defined as a matrix of parameters, allowing the architecture to respond to daily patterns of each individual in the network. Additive manufacturing in clay-like materials using industrial robots is investigated as a fabrication technology that can deliver mass-customized integrated dwellings. First, to expand a bit on the larger discourse of this thesis, increasingly modern cities like London are laid out for people who fit into a certain demographic. Young, single, high-income professionals who have very flexible lifestyles thrive in this environment. But what about the ones who are not so lucky to fall under this demographic? This thesis investigates possible solutions for a user base that typically makes up the backbone of local communities, yet is routinely ignored by commercial developers, craft workers, small business owners, stay-at-home mom and dads, artists, people who are less flexible and tend to stay in one community for a long time, who contribute and depend on these communities for their livelihood. In the UK, an estimated 25% of the working population does some kind of work at home for at least 8 hours a week, but most housing projects do not address this segment at all. One way communities have successfully created their own homes is with co-housing. The term is used to describe a model where communities self-finance and build homes, cutting out middlemen with commercial interests. In the UK, there are about 60 registered co-housing projects, some of which can be found in London, but it is far from being the norm. We see an opportunity here to reinvestigate the live-work topology in combination with co-housing in order to create an alternative housing model.
At the base of the research lies the hypothesis that human settlement patterns need to become intimate reflection of their communal structures in order to form strong, sustainable communities. Historically, humans have lived in cohesive communities where they dwell and work together intimately. This is reflected in the architecture, which takes specific forms based on the community. We have looked at different ways to understand and analyze these patterns. Insight gained from complex network analysis methods and space syntax help us develop the operational tool to approach architecture from a social angle. The vernacular working home, as outlined by Frances Hollis in her book Beyond Live Work, provides a base typology for custom-tailored homes. Historically speaking, there's a wide variety of custom-tailored homes that are optimized to the user needs. For example, the English Topshop or the Japanese Machiya are highly successful counterexample to the generic developer blocks. Prior DRL project, RAMTV explored idea of working with a network of users in order to tailor negotiated mass-customized solution. R50, a co-housing project in Berlin, provides insight into how to design for communal building projects. The highly successful German Baugruppen shows how to engage with an existing community and deliver user-centric housing. And also, there's a huge potential in freeform 3D printing, as it can collapse several layers of complexity in fabrication process. However, 3D printing at the architectural scale is still in its infancy and lags behind the engineering aspect. Our focus is on design application. As our architecture is a compression-only system, unreinforced masonry construction provides insights into geometrical constraint. The geometries developed by Gaudi, Guastavino, and Dieste provide case studies. Now coming to the project, the process can be broken down into 3 levels of development: the larger organizational level at the building scale, the unit level, which looks at the individual homes, and the structural levels, which deals with the construction system.
All right, starting with the organization. During the research process, we have identified sites of varying nature. Our current testing site has been chosen for several reasons. It is located near Elephant and Castle in London's Southwark district. It is currently occupied by a luxury apartment complex, which is the standard type of development found in London today. We are borrowing the site to propose a hypothetical alternative that could bring more to the local community. It is located right next to Pullen's Yard, a 19th century housing block purpose-built for craftspeople and traders. When manufacturing disappeared from this area, the workshops have been converted by artist designers and artisanal professionals into live workspaces. Today, the complex remains an important anchor point for the local community, providing services and public events. We see our proposal as a contemporary addition to the community, reinforcing this vernacular typology rather than push it out of the city. The site is shared by 3 different communities, each with its own identity. We focused on one of them for the design development. This prototypical community consists of 16 households or 35 people. Through a series of conversations and questionnaires, relevant data is captured in the relational roster. For each household, we record its existing size and composition. We also record the characteristics of the previous home and the desired spaces and their square footage. With a relational bubble diagram, we also capture how these spaces should be related to each other. Some households may be willing to share spaces in order to cut down on cost, but they might also have some kind of symbiotic relationship. For example, one of them could be a caretaker and the other an elderly person. In the same manner, the community is interlinked through a network of productive relationships. The graph is useful because it allows us to capture all relevant information into one data structure that can be operated in an algorithmic way. The graph is multi-scalar, revealing more and different information as you zoom in. However, for the computational side, all that's really needed is a data matrix that records the connections and type of each node. One example is shown here on the screen. Coming back to the site, it is first subdivided into a 3-dimensional grid. The grid acts as a world for a growth algorithm to operate in. A pathfinding logic is then used to generate schemes. Basically, we have a starting point where pathfinding agent is seeded. Following its rule set, it places units at a specified interval, traversing over the site. The rules are simple, but they can be stacked to form more complex behavior. For example, turn randomly left or right when hitting a boundary, or branch every time a unit is placed. These rules give us distinct tree-like structures, which become the circulation of the building. The movement is further controlled through a cost-to-move system. For example, traveling vertically carries a much higher cost than just traveling horizontally. For a test site, we use the rule, nodes are sorted by largest amount of connections, branch every time after a node is placed, and every unit has to touch the parameter. Here's the same process shown again with each unit mapped. The growth logic is additive, so the placement of each unit is affected by the ones placed before it. Simply put, the algorithm can be explained as a game of Tetris in 3 dimensions, with the rule set as an operational driver. Here we have applied a different rule set to each site. You can see the resulting growth trees are very different from each other. The growth trees can be interpreted as the quality of the space. For example, site 1 has an active center hot zone, where site 2 has a more distributed scheme with active pockets. Site 3 has a very active parameter with a private center.
Now coming to the unit level, based on the rule set, we get an organization of spaces that satisfy the requirements of the community. The actual units on sites are a negotiated result where site constraints, unit requirements, and shared activities come together. Using a relational model allows the unit to adapt to the site while still maintaining its important connections. From here, a low-poly version of the architecture is inserted. We have further developed a strip containing 5 units. The configuration attempts to match the original input given by the user, resulting in unique units that fit into each other. Shown here is the process starting from the initial data sheet and relational diagram to a 3-dimensional representation using metables, and finally the unit. Each home is customized based on the needs of the user. The unit comes with an extra programmable workspace And depending on the user, it interfaces differently with its surroundings. In this way, each unit is given a further level of customization. For example, this unit designed for Conway, who is a writer. The workspace is on the first floor and faces to the courtyard, so it has no direct interface with the public, but it provides privacy and a good natural lighting. Similarly, this unit has a private office, but this time on the ground floor, facing out to the street. This configuration was provided for Bhooshan, who is a small business owner and receives clients often. Amy is a ceramic artist. Her unit is located on the first floor, facing the busy first floor common space, giving her works exposure to the local community while also helping her to build connections. Richard operates a small coffee shop on the ground floor, facing out to the street. He also helps Amy sell some of her work on the site. Alexandro is the community manager. His workspace is on the ground floor, directly opposite to the common meeting space, thus making him easily accessible to the community. So shown here is a shared living room between two units. The articulation of the branching of the ceiling allows different level of light to reach into the unit, thus allowing us to optimize it for the activity underneath. Here's the living area of the single unit. Here you can see how 3D printing is used to print different elements of the building, such as the windows, walls, stairs. The break lines of the 3D printed segments become an architectonic feature of the space. This is section cutting through the center of the site. The interstitial spaces become communal areas where residents interact with each other and visitors. In the scheme, this is mainly expressed in the very active courtyard where most shared activities happen. Here's a perspective view of the courtyard from the first floor, showing the more varied conditions of the center hot zone in this scheme.
Lastly, we come to the structural level. Using 3D printing, we aim to simplify the construction process as much as possible in order to make building homes less reliant on developers, while still maintaining a highly customizable system. We have developed process where, starting with user requirements and social relationships, a building organization is generated. Using the edges line of the cubes, primary compressive forces are calculated for structural integrity. The resulting geometry is further segmented. Function and textures are added at last. The grid-based organization was chosen because it is developable, meaning we can extract structurally sound geometry. Here you can see how a single cell can translate into a variety of different structures, going from grid to structural center lines, to low poly geometry to segmented printable pieces. 3D printed clay and similar materials are very weak in tension. That's why we are borrowing insights from the unreinforced masonry construction and other compressive systems. The grid-based aggregation allows us to extract center lines that line up structurally, thus optimizing the geometry to its structural qualities. We use 3D printing as the main fabrication technology because it removes degree of separation between the end user and the construction process. Highly customized and very differentiated geometry can be fabricated without any added complexity. Using one single construction system for most architectural elements simplifies the process considerably, thus minimizing cost and effort, making it viable for a wider user base. In terms of construction, we are proposing an on-site fabrication system where the whole construction assemblage comes as a streamlined package, portable on standard cargo truck. We chose to develop pneumatic system with clay as base material because of its low cost and because it can be built using the limited resources that we have. Clay is also easy to find locally, not to mention that it is the oldest building material in the world. We also understand clay as a proxy material for materials with similar behavior but much higher technical difficulties, such as concrete. It is important to mention that the material has inherent limitations. Not everything is printable. The first step for us was to establish these limitations. We have developed parameters in order to build a geometric system that is inherently constrained by printing limitations. Parameters that we have tested are maximum overhang angle with simple layer by layer, maximum angle using non-horizontal planes. Here we have also discovered that the accuracy of the tool center point, or the TCP, matters. Same experiment with fixed TCP adjusted to the shifting planes. And also flying layers for openings or perforations and its capacity to recover. Branching geometries using non-continuous printing. So based on these tests, we get certain forms that are printable and useful. "3D printing makes it possible to fabricate different elements of building using one method that includes structural elements such as column, walls, and floor support. Performative elements such as different ways to create openings for light and ventilation, mechanical elements for plumbing and electricity. And ornamental elements, which basically comes for free as side product of printing process. The structure is segmented and not printed all in one go because of material limitations and because printing at an architectural scale has complexities that are hard, if not impossible, to resolve with one solid print. First of all, segmentation allows us to limit failure to local prints instead of the whole structure. Secondly, timing is very important with materials that need time to dry or cure. With all of our larger prints, we have to let it dry periodically and after a certain height so it can support its own weight. And third, with our branching structures, choreography is an essential part of the print. For example, save point have to be added in order for the robots to avoid crashing into the print. As a result, we have developed a process where the structure is printed on site, but it's segmented in time. The first shows the printing process of our final prototype, where we tried to combine all the techniques we tested. It is one single object, but segmented into 4 prints. In between, it is allowed to dry, but also it optimizes the toolpath for the robots. The size of segments depend on the material. For example, glass has to be printed in high temperature environment, and it's inherently limited to a kiln, whereas concrete can be printed at much larger scale. To this end, we studied different ways of segmentation and how to resolve connection points. This video shows the construction sequence of one unit. Starting out, the truck carries the robotic arm and constantly calibrated by beacon signals. The segments are printed following the choreography of the robots. Shown here is the printing process of the main structure. So this concludes our presentation. We'd like to give special thanks to our tutors, Theo, Shajay, and Alicia for their insights and advice, and AKT2 for structural consultation. Also Angel for generously letting us go wild in the robot room, and of course our phase 1 helper, Sam, Cesar, and Charlie for helping us pulling together at the end. Thank you.
So right here it's a series of studies model that we done with the flying layer for the opportunity to create a preparation and an opening. This is the series of study for the layer by layer overhang, how much angle can we go. And this one is a series of branching model where we study with the choreography of the printing robot. This one is the 1 to 25 model of some units in our scheme, printing by plastic, and this one is the clay version of it. This one is the pneumatic clay chamber that we developed, and this is the series of plane shifting study to see the limitation of the printing of the material. And right here is the picture of our 2 big prototype that we cannot have today. This one we done in the Boston, and the other one is, unfortunately, it's collapsed during the New Year break. And this one is the segmented model when we consider the center line, the cutting line to counter the center of gravity to achieve the column 2 slabs.
Well, it's really fantastic, absolutely amazing. I mean, the last team before lunch hit us with this kind of fantastic entertainment and visualization and bringing it home, but I think you're hitting us with the most mature, intelligent, worked through proposals which could step into market right now, but be disruptive in that market. I mean, I'm very, very impressed what you're doing, and I think it's 2 projects, but I think the way they converge is very, very important and strong. You have that very sophisticated programmatic entrepreneurial venture, the social network logics, not only the idea, but the way you bring in data in a sophisticated way, the way you then use sophisticated computational algorithms. You also know the history of some of that from Hilliard and social library space. Actually, Julia is sitting here who's contributed to this, and it's great to be an institution where you have that kind of depth of experience, and then you have that amazing research on the 3D printing, but folding in with the sophistication of Philip Block research group, structural logics, compression only. I mean, there's so many comes in, and it's also should become clear that this couldn't have been just 3 students. There's a kind of depth of history within this room and within support systems. It comes together something absolutely compelling and unique, I think, in the kind of world of students. And how these connect clearly is, of course, there could be many different systems which could connect to this, but it had to be a parametric system, because the variability and depth and intricacy of tailoring you talk about on the social side, on the programming side, is matched up with the huge amount of variability and the tailoring capacity and last-minute readaptation on the fabrication side of things. And this is a kind of super tailored, yet through robotics, it will be as cheap as mass reproduction, because once you have invested in the robots, and if we always asked, you're always challenged with this in terms of cost, this is actually going to be cheaper than anything else, because there's also structural optimization, minimizing material. It's kind of really on-demand processing where you don't have to have big stocks. It's kind of the kind of Toyota model of delivering just in time is in that. I mean, it's really very, very sophisticated and compelling. I mean, wow. I had one question though. How are you burning these pieces? Where's the oven?
Yeah, so we're thinking it's a set of materials. So clay, we're looking at kind of vernacular mud homes, which don't have to be fired. But then, obviously, pieces that are exposed to the element have to be weather resistant. So those would be either in concrete or maybe like shingles in fired clay, which is basically ceramics. Yeah. But obviously, however big the oven, it has a size limitation.
Yeah, I wonder if you could kind of just mix materials, you know. Could something be self-fusing, self-firing? I don't know, is there something, you put phosphor into it, or something that is not dependent on an archaic process like a kiln? I wanted to ask you a question too. In your process, which is very accomplished, by the way, how have you felt about imprecision, about imperfection? Because, you know, we live in an age of really high emergent perfection in the things that we build. What's your feeling about that as architects?
I think we can live with it. I mean, part of the printing process, you just inherently get mistakes in the print, and those actually can become really beautiful textures, for example. So it's kind of like an added bonus to what's being built.
I think, you know, I mean, it was really super amazing. I think, though, in the end, for me, one thing that was missing to all this sophistication is a level of control over these, I mean, not mistakes, imprecisions in a way, which are inherited from the process, but you have no control over them. And I think would be quite interesting to perhaps have some kind of computer vision system to help you understand exactly what this material is doing while you print it, especially as you want to bring things on site, and probably a robot cannot really be registered so easily on top of a, you know, a machine like that. So I think you need some kind of computer vision system, and maybe in this case you could really control these imprecisions and control the aesthetics, which at the moment is a little random in a way.
There's something that struck me, and it struck me yesterday in one of the projects as well, the folding aluminum surface yesterday, which looked like tailoring, like making clothes rather than building. And here again, you have something very interesting. Let's assume robots are modern technology. Let's say 3D printing is modern technology, and you have modern technology producing a vernacular image. And I find to some extent that the apotheosis of modernity would be to get rid of the look we all associate typically with modernity, a very fascinating thing. And on top of that, you know, looking at these spaces, I mean, they're phenomenal living spaces, actually, and they look highly traditional, highly homely, with an extreme sense of belonging, beautiful, very, very spatial, old-fashioned, but they're the result of an old-fashioned type of space, which is a result of the newest technology. And I find that a wonderfully explored paradox, and I think your project, in a way, illustrates it beautifully.
Yeah, I think there's also a limitation in this to some extent, because if you look at what Philip Block delivered in terms of Reinhold and his conceptualization and algorithmic translation of compression-only systems, that he can take the plan libre, the free plan, and yet optimize a shell configuration onto that. And that will look very organic and very different. Why this comes out, I mean, it's cute and it's elegant. In your case, since you went for the simple model, you went for the cubic base frame and maintain a lot of symmetry in the individual units, there is variety, which I love, and I wonder where this is coming from, because you have many different ways of covering, so that indicates it's not a single optimization. So that's something you maybe want to address. But I think, yeah, that paradigm of the compression-only way we can do that now can be much more free-form and organic looking, and you could overcome, if that was a problem, the traditional vernacular look, which is based on that base module. And maybe the base module was, in the end, something you could have also questioned. And there will be larger spaces where some of these cubes congeal into a larger, maybe more amorphous footprint, social space, and at that point you would have a rather different vaulting pattern emerging.
Just as Patrick's explaining that, I'm quite interested in material morphology. I can't stand things which are sort of just made out of one material. We are not. So, you know, there's that idea that you, maybe for the higher compression spaces, you use concrete. And as you move up the scale in a, you know, tour sans fin, the Nouvellian way, you know, you're applying, you know, fenestration to, you know, to these structures. But, you know, you could look at that morphology of density, weight, and light. And I think it's amazing, because I think it's so buildable. I mean, I could see this made, and you've got to build something. You do. No, because you've harnessed everything, what Neri was doing and everything. I mean, it's all there. And I think as we were explaining, there's a whole new dialogue between, you know, past, present, future. It's a sort of fast forward, pause, rewind thing going on, which we need to do, I think, within the fields not only of architecture but design.
Yeah, I want to congratulate you for this research, which, as what said, is really good and really substantial and precise, actually. I mean, realistically speaking, this thing can be built. I mean, with concrete 3D printing, and I know a bit about it, obviously. Yeah, I don't think my company can sponsor such a big thing, but basically, its technology would definitely allow it in any case. So, what I mean is that apart from that, from the fact that you started from scratch, you have been your own extruder, you have made a very interesting research on morphologies, etc. I still wonder why we should only address the issue of 3D printing through a compressive-only logic. I think at some point it's a limitation in the possibilities. Obviously, it's a solution which comes to mind at first, actually, because these materials have absolutely no performance, no capabilities for tension or even sometimes torsion. It's pure compression, even if clay is in fact more or less nothing, because I mean, unless it's fired, the mechanical properties, if you don't add some other material into it, are really, really weak, actually. But I mean, probably now it's time to engage into an approach of 3D printing which is more hybridized, which is also making use of some other constructive components, which is making use of other paradigms. I mean, and also because it's lovely, but at some point in terms of shape, it always brings us back to this kind of shells and church-like morphologies. And I mean, ultimately, I think we should now engage 3D printing with more paradigms and saying, okay, compression is fine, but even if we fail, let's try to add some other structural dimension to this logic. Otherwise, we might stick to this vault and compression only aesthetics maybe too long. But I mean, the research is just like amazing and super strong.
It brings to mind, I mean, what Ross is saying, there could be multiple materials, the same system could deliver concrete and then it could deliver the clay on top. And I mean, these experiments here with the cantilevers, you actually will need tension, a tension ring, and that part could be up to here, it's concrete, and then up on the next level, it is going to be clay. And we do like the constraints coming in. The material constraints, the structural constraints, the fabrication constraints, that's where we like these lines. and we might start to like certain deviations, but also what you have here is deliberate ornament, slowing down the drooping, this kind of material computation is in the model. And the more you have this, the more you will not notice anymore what becomes kind of defects and deviations. And then the concept of control comes in. But I think what is beautiful here is that the idea of factura, of tectonism, like we've discussed yesterday in the lecture, through the lecture, would become even more strong if you had two different materials. And then having a strong morphological bifurcation in the project of these two morphologies. And the idea of material dependency, and that correlates then strongly with materiality. So this idea of system correlation and morphology with materiality would become stronger if you had that idea, and you've talked about it. There will be concrete and there will be multi-material, and these materials will have then a kind of switching of morphological range.
Yeah, just to pick up on all the various comments that were said, like firstly, I'd like to commend you on like trying to synthesize the various ranges of research in like social networks and like printing, hardware development, like material mixture development, and finally even trying to attempt to physically express some of these things, like, and bring it together in geometry, etc. Like, so in that sense, it's very commendable. And having said that, like, there are a few things that I think maybe you can progress further, like in terms of like the final expression of things, to utilize all of these variability. To match that with the variability that's already in the community. Like, so you're doing that in terms of the size of spaces, but you could have kind of done that at another level further, like where you put this kind of ornament versus that kind of ornament, etc. Like, and that would have perhaps all of that variability is there in that particular render, but it doesn't seem as structured as the social network that it is housing, you know. So to build that correlation, I would think like would have taken like a couple of more iterations of that, like, but that limitation apart, but I would like to again commend you on like kind of trying to attempt at least synthesis, which was eluding you in the summer. So congratulations.
I think naturally what you're saying and what Patrick's saying come together. I think the idea of material appropriation and density relative to social networking function, dark spaces leading to light spaces. I mean, just that is incredible. Plus other things which affect us all. Recycling, it's all over the news right now, how we deal with polymers in society. I mean, it's an ideal project to bring in, you know, polymers into the equation as flooring surfaces, whatever. I mean, you can do other things with polymers. You know, obviously with the melt point, if you get, you know, thermoplasts, you can do that. And there's an abundance of material. I mean, you're working with materials which are ubiquitous. I mean, it's kind of incredible for that. I feel like it's a breakthrough, even though we all know this, we've seen it, but you know, it's that, this is, you know, the AA, and this is DRL, and this is where you're supposed to push it, you know, step it up, you know, in terms of how you mix these things, how you go beyond what we know, because we've been looking at the 3D printed concrete thing now for quite some time. So it's got to step up, and there are some issues, because if you don't fire that, then it's pretty much for hot countries. I think that's why when we look at it, we kind of imagine the Middle East, because there's something telling us that we have to naturally fire it. But yeah, that's all I wanted to say, is that just step it up into other material. Use it as an incubator for everything, social housing, the whole lot, really.